Hey there. I want to start today by talking directly to you. Maybe you're prepping for a massive meeting, maybe you're stuck in traffic, or maybe, and I have a feeling this is it, you are just feeling insanely curious today.
You want to know what makes the universe tick.
Exactly. Well, I have a question for you. What if the biggest mystery in the universe, the thing astronomers have been hunting for decades, isn't hiding in some deep, dark, distant void
What if it's right here?
right next to us?
Yeah.
And I don't mean figuratively. I mean, what if it's in a mirror reflection of our own reality?
It sounds like the plot of a science fiction novel, doesn't it? But we are actually talking about some very serious, albeit theoretical, physics today.
We are. Today on the deep dive, we are looking at the origins of dark matter. But we are not doing the standard, intro. No invisible glue talk.
Oh.
We're looking at new research from Stefano Profumo. He's a physicist at the University of California, Santa Cruz, and he recently published some pretty mind-bending ideas in Physical Review D.
And this is significant because Profumo isn't just, throwing ideas at the wall. He is looking at the fundamental crisis in modern astrophysics, the fact that we still haven't found dark matter, and proposing two very distinct, very exotic theories.
Exactly. So our mission today is to unpack these two theories. One involves a hidden mirror universe, which I have to say gives me major Stephen King vibes.
And the other involves the very edge of the expanding cosmos. It's a fascinating duality.
It really is.
You have one theory that looks inward, at a mirror universe sort of linked to ours, and another that looks outward to the cosmic horizon. Both are highly speculative, as he admits.
But they offer a completely new way to solve a very old problem.
Yeah.
So, okay, we've got mirror universes, nano-black holes, the edge of space. But before we get to the really exotic stuff, we have to set the stage.
Right.
We need to understand why a serious physicist is proposing something that sounds like it's from a comic book. Why are we so desperate to find this dark matter?
Well, it really comes down to a ghost in the machine scenario. We have a fundamental problem in astrophysics. Okay, our entire model of the universe, the standard model of cosmology, is built around the existence of dark matter. But here's the catch. It has eluded every single attempt at direct detection.
Which is just wild to think about. We're looking for something that, according to all this research, neither absorbs nor reflects light. It's literally invisible.
Precisely. It's invisible to our telescopes, our eyes. But, and this is the big but, we know it has to be there. And the reason we know is gravity.
Right, this is the classic spinning galaxy problem.
It is. If you look at these immense galaxies, they are spinning at incredible speeds, just unbelievably fast.
And based on what we can see, they shouldn't be able to do that.
Based on the visible matter, the stars, the gas, the dust, these galaxies are spinning so fast that they should just, tear themselves apart. They should disintegrate.
So it's like putting a handful of sand on a spinning record player. You spin it too fast, and the fan just flies off.
That's a good analogy, a really good one. But these galaxies aren't flying apart, they're holding together.
So something must be there, acting like a glue.
Exactly. Something is generating enough gravitational force to hold it all together. That something is what we call dark matter. It provides the extra mass needed to keep the stars in check.
So we know it's there because gravity says it has to be. But we can't see it. This has been the deal for decades. Why the pivot now to something like mirror universes? Why not just keep looking for the particle?
That's the key insight here. For the last, 30 or 40 years, the smart money was on something called WIMPs.
Weakly interacting massive particles.
Right. The theory was elegant. There's a particle we haven't seen yet, it's heavy, and it just floats right through us. We built these massive detectors deep underground, huge tanks of liquid xenon, just waiting for a WIMP to bump into an atom.
I've seen photos of those. They look like sets from a sci-fi movie.
Yeah.
And what happened?
Nothing.
Seriously.
Absolute silence. The experiments, like LUX Zeppelin, have become so incredibly sensitive, and they haven't found a single thing. This WIMP silence is causing a bit of a crisis in physics.
It suggests our main guess might just be wrong.
It does. It suggests we've been looking for a specific type of key, but maybe the door requires a combination code.
And that's where Profumo's research comes in. He's saying maybe we're looking in the wrong universe entirely.
Exactly. If the particle isn't here in our standard lineup, maybe it belongs to a different sector of physics.
Which brings us to the first theory, the dark mirror universe.
This is the idea that dark matter might be hiding in a dark mirror universe that is contained within our own visible universe.
Okay, stop right there. Because when I read this, my brain immediately went to pop culture. And the article actually makes a direct comparison that I think is just perfect.
I saw that, yeah.
It brings up Stephen King's The Dark Tower.
It's a very evocative image.
It is. The source describes it like one of King's mirrorverses. You know, imagine a shadow version of the same fugitive chasing the same man in black across time and space. This idea of a parallel existence that mimics ours but is just dark.
It's a compelling visual, for sure. But if we strip away the fiction and look at the physics, it's actually grounded in something called quantum chromodynamics.
QCD.
QCD, yeah.
Which sounds terrifyingly complex. Can you break that down for us without breaking our brains?
I will do my best. So Profumo was inspired by QCD because it explains how the strong force works in our universe.
The strong force.
Right. It's what holds quarks and gluons together. Those are the building blocks that make up protons and neutrons.
Okay, so quarks and gluons make protons and neutrons. That's our stuff. The stuff we are made of.
Correct. Now, Profuma is suggesting that this dark mirror universe would have its own versions of these particles and forces. They would act in the same way, but they'd be, dark.
So we're talking about dark quarks.
And dark gluons, yeah. In this mirror universe, dark gluons would bind dark quarks together to create dark baryons.
Dark baryons. And in our universe, baryons are things like protons and neutrons.
Exactly. So these dark baryons would be the mirror image of the protons and neutrons we can detect. They form the structure of this hidden universe. It's like a shadow reflection of particle physics as we know it.
I want to make sure I'm getting this. He isn't just saying there's magic stuff out there. He's saying, what if the same laws of physics that created us happen twice?
That's the beauty of it.
Once for us and once for this dark sector.
It respects the symmetry we see in nature. But, and this is crucial, there is a difference. In our universe, baryons formed stars, planets, and us. In Profumo's model, the dark baryons behave differently the very early universe.
How so?
It has to do with how they clump together. Profumo theorizes that if clouds of these dark baryons became dense enough, really massive, they wouldn't form stars. They would have just collapsed in on themselves.
And when things collapse in on themselves in space,
you get black holes. Specifically in this theory, nano black holes.
Nano black holes. I have to say, that sounds both terrifying and adorable at the same time.
Well, don't let the name fool you. Their impact would be massive. Now, it's important to note, and the source makes this distinction clearly, that theories about primordial black holes being dark matter have existed before.
Right.
But usually, researchers saw them as products of, not with light, no. But we can hear them, in a sense.
Hear them.
Profumo suggests a potential detection method. The merging of these dark matter black holes that could generate gravitational waves.
Gravitational waves. Ripples in space-time.
Exactly. When two black holes spiral into each other, they disturb the fabric of space itself, sending out these ripples. And we now have detectors, LIGO and Virgo, that can pick them up.
But wouldn't a dark matter black hole merging sound the same as a regular one?
Not necessarily. Because these are nano black holes, they are much, much smaller than the ones formed by dying stars. Their chirp, the frequency of the gravitational wave, would be distinct.
A different sound.
A different signature. Profumo is suggesting that future detectors might pick up a specific signal that basically screams, mirror universe.
So we aren't looking for a particle in a lab anymore. We're listening for the crash of invisible black holes.
That's the shift. It completely changes the hunt.
That is absolutely mind-blowing. But Profumo didn't stop there. He has a second theory, and honestly, this one feels just as wild.
It does. This second theory pivots away from the mirror universe idea and looks to the very edges of reality.
Right. The cosmic horizon. This sounds like a philosophical concept, but it's a physical place, isn't it?
In a manner of speaking, yes. The cosmic horizon is essentially the edge of the observable universe. It's the point beyond which light hasn't had time to reach us since the Big Bang.
Okay.
Profumo's second idea is that dark matter particles could have formed at this edge.
Walk me through this. How does the edge of the universe make stuff? I think of the universe as a container that stuff is in, not something that makes stuff itself.
To get it, we have to go all the way back to the Big Bang. The universe went through a phase called accelerated inflation just after it was born.
This is when it expanded really, really fast.
Incredibly fast. In fact, Profumo argues that initially it was expanding faster than the speed of light.
Wait, faster than light? I thought that was impossible.
Objects within space can't move faster than light, but space itself can expand at any speed it wants. It's a tricky concept.
It is.
But here is the key mechanism he proposes. He uses an analogy that I find really helpful. Hawking radiation.
Oh, right. Stephen Hawking. Black holes again?
Yes. Hawking radiation describes how particles can essentially evaporate from the vicinity of a black hole's event horizon.
Okay, can we do the I'm 5 on Hawking radiation.
Yeah.
Because I always nod along, but I'm not sure I really get it.
Sure, let's try. So imagine empty space isn't actually empty. In quantum physics, empty space is just boiling with virtual particles.
Okay.
Pairs of particles and antiparticles that pop into existence and then immediately annihilate each other. They cancel each other out.
So space is fizzy, pop, gone, pop, gone.
Exactly. Now imagine this happens right on the edge of a black hole, the event horizon. One particle falls in, but the other one escapes. They can't cancel each other out anymore. The one that escapes becomes a real particle.
So the black hole essentially rips the pair apart and spits one out into the universe.
In simple terms, yes. Profumo thinks the cosmic horizon, the edge of the rapidly expanding universe, acts like a universe-scale equivalent of a black hole's event horizon.
Whoa! So the edge of our entire universe is acting like the edge of a black hole.
That's the idea. Because the universe was expanding so fast during inflation, it created this horizon. Virtual particles at that edge got separated. One stays in our observable patch, the other gets pulled away by the expansion.
And the result is?
Real particles are radiated into existence.
And these particles are dark matter.
They could be. Profumo argues that heavy dark matter particles could be produced purely by the geometry of this expansion. No collisions, nothing else required, just the universe stretching so fast it rips matter into existence.
So dark matter is basically leaking into the universe from the edges.
That's the theory. And here's what's really fascinating about it.
Go on.
This isn't just ancient history. The source points at a surprising fact. This process might still be happening.
Because the universe is still expanding.
Exactly. We know the fabric of space-time is still expanding. We see the evidence in the increasing distance between galaxies. Profumo argues that as long as this expansion continues, dark matter should continue to be radiated.
So the universe is essentially a dark matter factory, just churning it out as it stretches.
It's a continuous production line driven by the geometry of the cosmos itself. It implies that the amount of dark matter isn't even fixed. It could be increasing.
This is a lot to take in. We have a mirror universe full of nano black holes on one side, and a universe that sweats dark matter as it grows on the other. But we have to ask, is any of this real? Or is it just math on a chalkboard?
That is the most important question. And to his credit, Profumo is very transparent about this. The source material notes that he admits both theories are highly speculative.
Highly speculative. That's scientists speak for, we can't prove this yet.
Right. Essentially, yes. But he also notes he doesn't consider them impossible. And that's a crucial distinction in theoretical physics. You start with what's possible within the known laws of physics, like QCD or general relativity, and you see where the math takes you.
And if the math holds up,
it's a valid candidate, even if it sounds wild. He also noted that the underlying mechanism for dark matter production remains an open question and the subject of intense scrutiny.
Right, so we haven't solved it. But what Profumo is doing is widening the search area.
That's it. He's telling us to stop just looking for a specific particle under a microscope. He's suggesting we look at the structure of the universe itself, at gravitational waves, at the cosmic horizon.
It feels like a huge shift in perspective. Instead of asking, what is this little speck made of? We're asking, how is the universe actually built?
And if we connect this to the bigger picture, it just reminds us that our assumptions about the dark sector might be way too narrow.
We assume dark matter is just stuff like our matter, only invisible.
Right. But it could be a byproduct of a completely different set of physical laws or a consequence of the universe's own expansion.
It definitely makes the universe feel a lot more crowded in a good way. Or maybe a spooky way, if you're thinking about those mirror coasts.
A little bit of both. It highlights that empty space isn't empty at all. It's potentially filled with the echoes of a mirror reality or the radiation from the universe's own growth.
So what does this all mean for us, for the person listening right now?
I think it's a reminder of how much we still have to learn. We often think of science as a finished book. We know gravity, we know atoms, but here is something that makes up the majority of the mass in our universe, and we're still debating if it comes from a shadow dimension or the edge of time itself.
It's humbling and very exciting.
Incredibly exciting. Every time we think we understand the cosmos, someone like Profumo comes along and says, but have you considered the mirror version?
So, to recap our deep dive today, we're looking at dark matter not just as missing stuff, but as a potential signal from a dark mirror universe populated by nano black holes.
Or it could be radiation coming from the cosmic horizon as our universe stretches out.
Two paths, both leading to a radical rethinking of our reality.
And both pushing us to question our assumptions about what this dark sector really is.
It's not just about finding a particle, it's about understanding the architecture of existence.
And waiting for those gravitational wave detectors to give us a ping from the other side.
Exactly. I want to leave you with one final thought, straight from the source material, because it really stuck with me. We've talked about mirror universes and shadow physics, but if a mirror universe controlled by the dark side of physics truly exists, is there a portal that leads us to it?
That is the ultimate question.
Perhaps that answer will one day come to light. Thanks for taking the deep dive with us.
Keep looking up.